So there's a couple of libraries. Probably the one that's easier to use is OpenConnect. It's available inside processing. You just download the library using the library manager. There's also Simple OpenNI. You need to have a look at how you install that library. With skeletal tracking, you get full positions of all joints in 3 dimensions. That means each joint has a time-varying 3-dimensional location. So it's quite a lot of data. Don't forget the Kinect has a limited range. It's about 3 meters or so. So you can't use it to work over 10 meters or 15 meters. You need to make sure you test it for the appropriate range of the system. As I mentioned, Kinect uses structured light, and that structured light has a limited brightness, and it only goes for a certain distance. It can also get quite confused by poor or very bright light, so if you use this system anywhere near sunlight, you'll probably have lots of issues. It's really designed for indoors, in like a lounge room situation without a bright light on the person that you're trying to pick up. Blob tracking is an alternative. That basically uses a camera. You look for blobs within the camera view, and you track these blobs as they move throughout space. You can do that using lots of different systems these days, and you basically only need a webcam to analyze the data. Here's a link to have a look at something. Optical flow is another approach to tracking. This is a little bit more low level. You don't require information about what the person is or their skeleton. You can track anything, but you're only really tracking it in very general terms. So the way optical flow works is that you look at pixels and compare frame by frame for the pixels, and you'll probably see that the color of the pixels moves in one direction if they're a moving object. So the pixels tend to move as a group as a person moves from left to right or from right to left or up and down. So that's optical flow, and it can be quite good for just working out how much movement is in the space and which direction it's going. It gives you data that you can use then to decide whether something's going up and down or backwards and forwards in a particular way. So it's quite robust against lots of different types of movement. If things in the frame aren't moving, they won't affect the optical flow at all. It'll only be affected by movement. One other technology that is getting quite popular is Leap Motion. Leap Motion is a motion tracking system designed to capture hands. So it's pretty small and easy to use. You get a lot of data though. You get lots of information about fingers and joints and wrists and other positions on the hand, all in one go. It's quite easy to use inside processing. Again, you just download the library. So what do you do with motion capture? So motion capture can help you with things like animation, with virtual puppetry or machinima, for instance. Motion capture is of course used in movies all the time these days, for any movies that involve a lot of CGI with characters. Motion capture will often be the main way in which they capture the acting of the performers. You can use motion capture within games as well. You can use it for music and dance. You could use it for security as well, and biomechanics to work out whether someone is who they say they are. You can actually understand a lot about a person and a lot of unique things about a person by looking at their motion. Motion capture works best with continuous links between the gesture and the sound or visuals. It doesn't work very well with buttons, so try not to use motion capture for buttons. They can be error prone because you might think they're in a particular location, but they're actually in a slightly different location, and therefore you end up banging on the wrong location. And because we're just capturing motion, there's no feedback to tell you that you're hitting the wrong location, really. So it can be quite frustrating for users if you use virtual buttons. However, Kinect and Leap capture gestures, wide, continuous movements through space quite effectively, and you can do quite a lot with those. So think a bit about how you're going to design your motion capture system if that's what you're going to do. So here's a continuous relationship. You give a gesture into the system and it changes the output continuously. But here, if we have inputs that are discrete positions, it's going to be very hard to move between those discrete positions precisely. We're not very good at positioning our limbs in particular locations in space. Instead, we tend to do things that are relative to each other rather than discrete positions. Here's a simple idea about how we can map data. So we have gestures that go into a gestural controller, which understands the gestures and turns them into numbers that represent the gestures. So you might be looking for things like overall movement in the gesture, or whether the gesture is moving up or down overall. And that then is passed to particular elements of a sound production system, and that may be a sound synthesis system or a sound playback system, and that creates sound, and that sound goes back to the performer, and the performer hears it and modifies their gestures in response. So it's important to think about what type of feedback are you giving back to the user. How are they going to know what they've done and whether they like what they've done? With computer games, you have visual feedback, but you also have haptic feedback with the controller, and you have sound feedback as well to tell you that you've fired the laser or something like that. So you have a lot of different types of feedback to help you navigate the experience of using a computer game. Similarly, you need to think a bit about how that's going to work. For gestural controllers, complex cross-coupled mappings are usually perceived as being more expressive. You've got to be careful when you make a mapping from motion captured data that is not too simple and too obvious. Something where you move your hand up and the sound goes up, and then when you move it down, the sound goes down. Yes, that will work, but it will get boring really quickly because you move your hand up the second time and the surprise is not there anymore. You move it down, up, down, up, down, up, down. You don't have much freedom to create lots of different sounds because every time you move your hand up, the sound goes up, and every time you move your hand down, the sound goes down. So we need a little bit more control over the types of sounds we can produce for it to be engaging and for us to want to use this system for to create some sounds or to control your experience. So here we can have a look at a mapping for a trombone. So a trombone has the hand's Y coordinate, and it could be used to control the pitch or the volume. But similarly, we could use that hand Y coordinate to control other things about the experience, such as the color or the brightness. The rest of this lecture is devoted to demos, and it's probably best you pull out the slides directly and follow the links. Alon Ilsar is a PhD researcher at UTS, and as is Andrew Bluff, who's now a postdoc. This work uses their motion capture system called the AirSticks. There's two controllers here that are used to play a drum-like system. Here we've got some examples of scanning 3D environments, and 3D scanning is a really interesting new technology that can be used within a motion capture context. Encoded is a large-scale dance work produced by Andrew Johnston and Stalker Theatre. It uses projection mapping as well as motion capture systems in a great deal of detail. Here's a bit of an example of how it's all put together. This Dubstep Connect system is a pretty good example of how to make a really exciting video. It is a bit of a cheat though. They're not all it's not all done live. Some of it was faked a little bit. This example is a really interesting face tracking system that allows you to look at how open or closed the mouth is and position of eyebrows relative to eyes, from which you can gather a lot of information about speech and motion. So going a bit further, you can even do things like face substitution, where you put someone else's face onto your face or another person's face by knowing where precisely all of the parts of the face are at each time. Finally, this link here is a link to a really interesting documentary about Trimpen, who is a famous robotic artist, robotic sculpture artist. So have a bit of a look at that at your own pace. Hopefully it'll give you a few ideas about how to devise ideas for your project.